11th day of the 50 days of tutelage, and today we're going to be doing Newton's laws of motion. Newton's laws of motion. We started talking about kinematics in the last class, and in this particular class, we'll be talking about what exactly brings about motion. Because without um, motion, there's always a cause for motion, and then without this that I'm about to discuss today, there won't be motion. So let's get right into it. So Newton's laws of motion. So before I proceed forward, the major thing we'll be talking about here is the concept of force. Is the concept of force. So motion would not occur without the presence of force. It is force that is impressed on a body that causes it to either move or not move, as the case may be. And this force, we have the different types of forces. We have the push or the pull force. This one talks about the contact force, where you have to be in contact with the object before you can apply the force. So if this is the person applying the force, and then the person that is being the force is being applied to is C, so you have to be in contact before you can push or you pull them. And then we have what we call force field as well. I'm not talking about force field today. We have different force field. We have the gravitational force field. We have so many things like that. But magnetic force field, electric force field. But I'm not talking about the force field today. I just want to go into the basic thing about forces that you need to know. Now, just like we have said, force is also a vector quantity. I think I mentioned that when I was teaching uh, scalar and vector. It's a vector quantity, and it has different dimensions. When I mean dimension, I'm not talking about the dimension that we discussed earlier. There are so many things that we use loosely in physics, and then we treat them as something entirely different. But what I want you to know is that all of these things are forces as well. So, for example, you have stuff like weight, you have tension, you have buoyancy, or sometimes some people like to call it upthrust, friction. So all of these are actually forces. So whatever you are able to do for force, then you are able to do it for all of these guys as well, and as many more as possible. So when I'm speaking about force, I'm going to be speaking in general, and I'm going to be talking about all of these guys. Although each of these guys, they have their different way where they perspective where they occur and all of those things. So, but we'll talk about a lot about it in this particular class. Now, let's go right to the Newton's first law. What is the Newton's first law? It basically tells us that if an object is at rest, or if an object is moving uniformly, it's going to maintain that thing until something else had what? Until something else had done work on it, or had tried to change whatever the way it is moving. So if an object is at rest, it should continue to remain at rest. So if it decides to change from rest and start moving, that implies that an external force had been imputed into the system. The body cannot just decide that it wants to move on its own. It doesn't happen. Another one is if the body is moving with a uniform motion, is moving uniformly already, it will continue to maintain that uniform motion. So let's say the body is moving this way, the body will just continue to move and move and move and move and move and move. But if it's going to change the way it is moving, whether it wants to stop or it wants to increase the velocity or it wants to decrease, whatever it is that it's going to do, there's going to be the presence of an external force being imputed into the system. That's basically what the Newton's first law is saying. And then that is where the inertia thing comes in. It's also called the law of inertia because inertia is actually, I would call it a state of reluctancy to change your present state. So I'm just trying to define it loosely. So when you say inertia, whatever it is that what your current state is, the reluctance that you feel from changing from that state to a different state is what we call inertia. So that is what the Newton's first law is talking about. So the presence of force which brings about change in movement of the body, or maybe the body is at rest or the body is moving uniformly before. So it is the presence of force that causes the change that you might experience in that motion. So that is that. Now the second law is where we actually like have more work to do, And I'm going to dwell a lot on the second one. So the second Newton's law of motion, that one says that the rate of change of momentum is proportional to force. Now, the rate of change of momentum, I don't want to talk about momentum today because I will still teach about momentum and impulse. That will be, I think, day 20 or so. But there's something that was derived there, which is the fact that F equals ma. So this is my major concern. Now, we say F equals ma. However, the statement of this law actually caters for what we call net force. It doesn't just say force alone, it caters for net force. And this is Newton's second law of motion. This equation represents Newton's second law of motion. But the first thing you need to get in the equation is that your F is always going to be the net force. That is, your F is always going to be the resultant force. Do not jump at any problem that has given you force and immediately you equate it to ma. Once you do that, you're already in soup. So the first thing you need to ask yourself is that, are there other forces in the system? In fact, if there is only one force in the system, what are the other things? How is it acting? Is it acting directly in the direction of motion? Or is it acting at an angle to the direction of motion? Or is it acting opposite to the direction of motion? You need to be able to answer all of these questions before you proceed and say F equals ma. Until you have been able to find the net effect of that force based on the direction of motion, do not equate it to ma. So therefore, this Newton's law of motion, the second law, talks about the net force being equal to the product of mass times acceleration. Now, it's a good thing that I've already explained scalar and vector, and I've already taught you how to find resultant of any vector. So everything that I've already explained about resultant of vector, you will need to apply them to forces as well. And I'm going to be doing some basic example in this video. So just make sure that you're following. Now, going from this now, I told you already that we have what we call weight, we have tension, we have buoyancy, we have upthrust, and we have friction. So quickly, I'm going to explain maybe a little bit of them, maybe like 3 or so of them before the end of this class. Now, let me start with weight. What exactly is weight? Weight is a force, and then weight is simply the what you feel when your mass is impressed by gravity. So the gravitational pull on your mass is what you feel as weight. So now it is always acting in the downward direction. It is always acting in the downward direction. So whenever there is an object, so if this is an object, the object is resting on a surface. Let's make that surface like this. So yeah, the object is resting on this surface. So the first thing you should note is that there is going to be weight on this guy, and the weight is always going to act downward. So the weight equals mass times acceleration due to gravity. So this is weight. But quickly, there's the third law. I think I need to bring in the third law in this case. The third law says that whenever there is an action, there is equal but an opposite reaction. There is equal but what? But an opposite reaction. So in this case, as the mass is being impressed on the surface is also going to react back on the mass. And then we call that a reaction. Now, this reaction, it can be in different directions, but there is a reaction which is perpendicular to the surface of interaction between this body and this floor. Then that is called the normal reaction. So a reaction that is perpendicular to the surface of interaction is known as the normal reaction. I'm still going to talk about this very soon. Now, having said that, the concept of weight, like I've said, is basically depending on the force of gravity. In fact, some people they call weight, they call it force of gravity. So meaning the effect of gravitational pull on any mass towards the earth, that is what you feel as your weight. So the weight itself that you feel is a reaction. So what you feel as weight is a reaction. Your weight does not change. Your weight is always the same. But under certain conditions, you feel maybe a little bit less of your weight or you feel a little bit more of your weight. These feelings are always governed by reaction. So reaction is what gives rise to the feeling that you feel about your weight. So whenever you feel like you feel less weighty, it is a reaction. Or you feel that you are weightier, it is a reaction. But your weight itself that is acting downward remains constant. It is the product of mass, your mass rather, and the acceleration due to gravity. So having talked about weight now, what about tension? Tension is actually such force that is found in spring, rope-like materials. And how do you generate tension? The minimum way to generate tension is if you have a string of, let's say this is the string, if it is fixed at one end and you apply a force at the other end in the opposite direction of the fixed point, then there will be a generation of tension. Tension is going to be generated in that string. So this is the way tension is generated. You have applied a force. So there's an applied force in this direction. Then tension is going to be acting in the opposite direction from where the applied force has been. So tension oftentimes, more than 90% of the time, always acts towards the fixed point. So you apply the force away from the fixed point. So tension will act towards the what? Towards the fixed point. Then you also have buoyancy as well. That one is going to be talked about in Archimedes' principle and all of that. Then we have friction. We have friction. So I'm going to be going into that detail of that friction properly. Now, what is friction? You see, as we have most of these forces here, most of these forces they are most times always favorable, especially when we consider them as a single force. When we are dealing with them as a single force, they don't necessarily lead to a disadvantage, but they can. However, there is one particular force. When I mean disadvantage, now I'm talking in terms of motion. I'm talking in terms of movement. I'm not talking about any special thing. Maybe friction allows us to move properly without slipping on the floor. No, I'm talking about actual moving. You are moving forward, you are moving backward, you are moving sideways. Whatever way you want to move, friction always stand as a disadvantage because it opposes motion all the time. Yeah, maybe the opposite of motion can now be an advantage at some time. Yeah, but this time around, the disadvantage I'm talking about is about motion. As long as movement is concerned, it opposes movement. That is what friction does. It opposes movement. Now, as it opposes movement, so every other force that wants to say they want to cause motion, frictional force tends to always act in opposite direction to the net force. So as we have F equals to ma, so you can still remember F net force equals to ma, then the frictional force is actually going to lead to a sort of deceleration. It's going to lead to a sort of what? Deceleration. That is what frictional force does. And so it is always kind of a negative force. It is always kind of a negative force. So now we have two, we have static force and we have the dynamic frictional force. I mean, static frictional force and dynamic frictional force. So the static frictional force is just it increases actually as you're going. It can start from 0 newtons. It goes 1 newton until it has reached the maximum force that is required to start a body, to just make a body start moving. So the force that is required to make a body just start moving, whenever you reach that force is the peak, is the maximum for static frictional force. So that implies that static frictional force varies from 0 when you have applied no force to when you have applied a force. So if you apply a force, so let's say the object is here now and you want to move this object, let's say the minimum force that will just make this thing start moving without giving it any further acceleration, let's say it is 50 newtons. Then what happens is that if you apply a force of 20 newtons and this surface is rough, there's a frictional force there, then the frictional force will also be 20 newtons. If you apply a force of 45 newtons, the frictional force will also be 45 newtons. But at a point, if you apply 50 newtons, the frictional force will be 50 newtons, and that is the static frictional force. Because what happens is that whenever you increase that force from 50 newtons and you just increase it by any amount at all, then this object is going to move. So static frictional force is like the maximum force that you need to overcome to just get a body ready to start moving. Then we have the dynamic friction as well. It is the friction that you consider when the body is already in motion. So the general equation that joins friction together and the reaction I spoke about earlier is that frictional force is proportional to normal reaction. So let me call the normal reaction, let me call it R. Frictional force, I think I should use N. Yes. Frictional force is proportional to normal reaction. So that now, if we now introduce the equation sign, then we have what we call a coefficient of friction. Coefficient of friction, mu. Mu, coefficient of friction, mu. Don't mind my mu. So, product of mu and normal reaction. That is what gives the frictional force. The question is that, how do we now determine normal reaction in all cases? I'm building a kind of case here because where I'm going to be ending this class is going to be on free body diagrams. Free body diagrams. So please make sure you follow everything I've been saying so far. And if you don't have your note with you, it is time for you to take the notes. And you can always rewatch the video over and over and over again to get proper understanding. And if you have any question, you can let me know in the comments. I'm going to respond to you. Okay, so back to what we're talking about. Now, frictional force is the product of coefficient of friction times normal reaction. So this coefficient of friction is just a way of telling how rough a surface is, or how rough what the interaction between two surfaces in contact. Because when it comes to friction, friction depends on at least two surfaces in contact. You cannot just have one surface, even though it's a rough surface, without the presence of a body trying to move over another, then you cannot see friction being generated. There must be a relative movement before you say there is friction. Okay, so back to this now. How do we now do normal reaction? And that leads me to free body diagram. So let's start with a body that is sitting on a platform. So if this body is sitting on this platform, the first thing you know is that as the body is sitting on the platform, there is one thing I call weight. The weight of the object is always acting downward. And as much as there are several reactions that are possible here, there are reactions in different directions, we are only interested in one reaction, which is known as the normal reaction. So the normal reaction is going to act upward. Whenever you hear normal in physics or math, it means perpendicular. So a reaction that is normal, so the weight is acting downward, reaction is normal. So whenever you have a body sitting on the surface, the two things that you should always generate force, that should always come to your mind, should always be these two. Don't compromise them. Now, when we're done with that, let's say I want to apply a force now. And for the sake of time, I'm going to be killing two birds with one stone. Now, let's say I want to apply a force, and I'm applying the force on the object at an angle, let's say theta, to the horizontal. So I've applied a force. So the question is that if this surface happens to be a rough surface, that implies that friction will be present there. And if friction will be present, the question is, what will be the direction of frictional force? All you have to do is find the intended direction of motion. So if this body were to move, where will it move towards? In this case, it will move towards the right. So therefore, the frictional force will act towards the left. So the frictional force is acting towards the left. So you can see the sequence, how the free body diagram and everything goes one after the other. So this is now where what I said earlier. I said the Newton's second law of motion, F equals to ma, is about net force and not just about ordinary applied force. So if you are given a question now and you had equated this F to MA, you would have been wrong. You were not supposed to be happy. You would have been wrong. So you don't want to be wrong. So now what do? We need to divide these things into horizontal and vertical components. So let's start with the vertical component. So the vertical component, the first thing you need to do is identify the forces that are acting in the vertical component. And the forces that are acting in the vertical component here, they are the normal reaction, the weight, and the force itself. See, the applied force, because it is inclined at an angle theta, it has a portion on the vertical. It also has a portion on the horizontal. Whenever a vector is inclined at an angle, so if you have seen the previous class, then you would know what I'm talking about. Whenever a vector is inclined at an angle, that implies that it has a vertical component and horizontal component. So that is why in this place I highlighted that there are three forces in the vertical component. Now, I'm not going to be explaining what I've explained in vector. So if you have not seen that video, you just go back to the previous physics class, then you see the video there on that, explaining how to find resultant force. Now, so in this case now, the three of them, we have N acting upward, so there will be normal reaction acting upward, and minus weight acting downward. Then this force is actually acting upward, so it's going to be plus, so plus F. But now I need to resolve it based on this angle. It's going to be F sine theta like that. I'm done with the three forces in the vertical. And I'm going to equate this to MA. What is M? M is the mass of this body. M is the mass of this body. And A is the acceleration in the vertical direction. But here's what you know. This body is resting here. There is no movement. It's not moving up. Neither is it moving down. So therefore, there is no acceleration. So this is going to be equal to 0. So I've been able to use Newton's second law of motion to derive that normal reaction will now be, if I take everything to the right hand side, that will be weight minus F sine theta. Now let's do for horizontal. For horizontal, how many forces do we have in the horizontal? We only have two. This F and the frictional force. So since we only have those two, F is acting to the right, but it is inclined at an angle. So I can have F cosine theta. Then frictional force is acting to the left. That will be minus frictional force. This will also be equal to MA. In this case, the mass still remains the same, but acceleration now is the acceleration in the horizontal direction. And there are so many things they could say about the acceleration. If they say that the body is moving uniformly, even though the body is moving, but it's moving uniformly, then acceleration will be equal to 0. I've also explained that in our class on linear motion, kinematics. So you should know that by now. But if they did not include that it is moving uniformly at a velocity of with uniform velocity, then acceleration cannot be 0. So therefore, horizontal equation will remain F cos theta minus Fr equals what? MA. And one thing you can do here is that you can now say that F cos theta minus, so Fr from what we said earlier is mu multiplied by N, coefficient of friction multiplied by normal reaction. So mu multiplied by, what is our normal reaction in this place? We have solved for it. That will be W minus F sine theta equals MA. And so here we have F cosine theta minus mu W minus mu F sine theta equals MA. So from the free body diagram, I've been able to get this equation for this motion. So that is exactly what you need to do. So for the sake of this class, I'm just taking this random and general example. Some of the other things that we need to also take note is that when you see tension, like I said, treat them as forces and just apply the second law of motion. If you apply the second law of motion, it just takes care of, you just need to know the direction in which other forces that are present in the system that they are applying. So for instance, let me just give you this last one before we wrap up this class. If you have, let's say, a body hanging like this, so this body is hanging. Of course, you know that as it is hanging, the weight of the body is acting downward. But since it's hanging on a thread, what will be up here is no longer normal reaction because it is not resting on the surface. No surface is pulling it back. However, like I told you, a tension will be generated in this string. And then if there's movement, you can now say tension minus weight equals MA. That is if the body is moving upward. If the body is moving downward, you do weight first. So wherever the body is moving towards is always regarded as the positive side. So direction of motion is better to regard it as the positive side. Although in a much more universal manner, right is positive, up is positive, down is negative, left is negative. And this is basically what you need to know about Newton's laws of motion. So the first law, the second law, and the third law. That will be the end of the class for today. I'll see you in the next one.